When we want to do a test to see if there's a statistically significant linear relationship between two quantitative variables, x and y, our general steps are going to be to state our hypotheses. Under the null, we assume there's no linear pattern. So we say that x and y are not correlated. Under the alternative, we're trying to find evidence so that we can prove that there is a linear pattern, so that x and y are linearly related, or they are correlated. Our next step would be to state our decision rule. So we'll reject the null if the p-value is small enough, right? If the p-value is less than or equal to some alpha level of significance. Our test statistic we'll get from StatCrunch, and that is going to be in what's called the slope row in one of the tables that StatCrunch produces, and you'll see this a little bit later on. So let's go ahead and go back through and work these steps out for the wolf data that we've been looking at. So under the null, we want to say that our two variables, tail lengths and weights of wolves, are not correlated. And then under the alternative, we're saying that tail lengths and weights of wolves are correlated. And at this point, we're not trying to specify that they're positive or negative in relationship. We're just saying that they're related. You can do a one-sided test if you wanted to, where you're saying that tail lengths and weights of wolves are positively correlated. So as tail lengths get bigger, weights get bigger. But typically what we do in linear relationships is just do the test for any relationship. The decision rule is to reject the null if the p-value is less than or equal to, and we'll just use a 0.05 level of significance. And then what we would do is run the analysis. So what we do is load our data into StatCrunch, go through the steps, and you'll be given these if you're asked to do this, and then look at the output. Okay, and there's several slides that have output on them that we'll talk about. At the top, there is some text that comes out of the window that pops up once you do the analysis, and it tells you what your variables are, your dependent or your response variable, your independent or your predictor variable, and then it gives you the equation of the line that best describes the pattern in the data. So there's some mathematical formulas and stuff that go into it, and we'll talk a little bit about the ideas of how it's done in a few more slides. But essentially this is the line that if you look at the scatter plot with the line drawn on it, this is what the equation of that line is. So we're going to focus on that line for one, and then the sample size tells you how many data points you had. The next two lines that are important are the correlation coefficient R, so that's your 0.6926 number, and then the R squared. And we'll talk later on about what R squared is in another video. The estimate of error standard deviation is used, except we don't really go into using the formula ourselves at that level. So we don't really use that number anywhere, but it is used in some calculations later on when we do what's called prediction and estimation, which will be covered in a different video. But the three lines of output we want to focus on for now are the equation of the line, the correlation coefficient, and the R square value. Then there's a table that comes out that says parameter estimates, and we want to look not at the intercept but the slope, because what we're really saying is that the predictor variable is multiplied by this slope, and if the slope is non-zero, that means the predictor variable has an impact on what's happening with the y variable or the response variable. So we want to look at that bottom row in this table. So the t-score we need is the number under t-stat on the slope row. So that's that 2.72, and then the p-value associated with that is the 0.0264. Now the t-stat you should be able to get if we weren't rounding estimates off and stuff, if you take the estimate over the standard error on the slope row. So 2.5 divided by 0.928 should give you the t-stat of 2.72, and I've rounded these off because StatCrunch gives them to several digits, and we just need them to, 1 or 2 digits is fine. The p-value, StatCrunch just has to look up for you. Now there's another table that can be produced if you ask it to do estimation, and it'll say predicted values, and it'll tell you what X value or what tail length you had. So this would be 16 inches, 24 inches, and 30 inches. And then if you just plug those numbers into that equation of the line, your Y values would be those next numbers, the 88.7, the 108.9, and the 124. Now the SE of predicting Y is something that has to do with that standard error that we talked about earlier that we really don't use, and the sample size and everything. But then you have confidence intervals and prediction intervals, so we'll have to talk about the difference in those later on. But this is something for the future, but this is just all the output that you could get. So to complete our hypothesis test, what we would need to do, so we left off where we had stated our hypotheses and given our decision rule. So then we would give our test statistic. So that was the t equal 2.72. And then the p-value, that probability, would be the next step. That's 0.0264. So then we make our decision. Well, 0.0264 is less than 0.05, so my decision is to go ahead and reject the null hypothesis. So there is evidence of a linear pattern. And furthermore, I can say that it's a positive linear pattern because the t-score was positive. The only thing that affects whether t is positive or negative is the numerator of the calculation, and that numerator, if it's positive, it means you see an increasing trend. If it's negative, you see a decreasing trend in the data. So we could write a summary that says at a 0.05 level of significance, there is significant evidence to conclude that tail lengths and weights among wolves are positively correlated. I could say they're correlated and then come back and say, furthermore, they're even positively correlated. But again, we can tell they're positively correlated since the t-score, or you could go back and look at the correlation, is positive. Now, if X and Y are found to be correlated, okay, statistically significant result from your hypothesis test, then we're actually going to say we'll fit a straight line that best describes what the sample pairs tell us and use it to draw inferences. So this involves a line of the form y equals b sub 0 plus b sub 1x. So the idea here is that you've got the equation of a line. Now in algebra, you typically hear y equals mx plus b. So m is the slope, it's multiplied by the predictor variable x, and then you add on a constant, which is the y-intercept. In this case, we switch that, and the reason for that is later on we can add more predictors in an advanced regression type model. The only thing we deal with in this class is simple linear regression, however. So the number that's by itself is the y-intercept. The number that's multiplied by your predictor variable, in this case tail length, is your slope. B sub 0 is your estimated y-intercept. That would be if you drew the graph out and you had the origin where the axes crossed and where the line crossed the vertical, the up and down axis, that is going to be what B0 is. Okay, now in practical terms it means it's what you expect on average the value of y, your response variable, to be if your predictor variable or your x variable is 0. The other number, the slope, B1, is estimated, and that sort of tells you, okay, how much does y change, and if it's positive it'll increase, if it's negative it'll decrease, every time you make x grow by 1 unit. So if we increase tail length by 1 inch, what happens to the weight of a wolf? Now in finding this best fit line, okay, in the background, what is applied is a method called least squares. The least squares means that if you determine how far from the line each observed y value is. So what's the difference between the actual y value and what the line says the y value should be at a given x coordinate? Then you square those differences so that negatives and positives don't cancel each other out, and then you make that sum as small as you can. And what this is, since you're solving for two variables, it actually involves some advanced calculus methods. Basically what you're doing is you're minimizing the squared deviations the points are from the lines. And there are mathematical formulas that have been solved, and they're programmed into software like StatCrunch. So what we're going to do is not worry so much about the equation and how to get it, but rather focusing on interpreting the slope and the y-intercept from the output. So for our example, you might remember that we had bold that weight was 48.4 plus 2.5 times the tail length. So the y-intercept is the number that sits by itself, the 48.4. Mathematically, it means if the tail length is 0 inches, right? So if the predictor variable tail length is 0, then that number, 48.4, is the y value. Okay, so if tail length is 0 inches, the weight of a wolf would be about 48.4 pounds. Okay, now this is inappropriate for a couple of reasons. Number one, the tail length is not going to be 0 for a wolf. If you go out and you see a wolf, they're not going to have a tail that is 0 inches long. Okay, so logically it doesn't make sense to see that in nature. But also, more importantly, what you want to focus on is our model was built using tail lengths that went from about 10 to 28 inches. If you go back to the scatter plot in the initial data set when it was displayed, you can see that the shortest tail length was 10 inches, the longest one was 28 inches, and you want to make sure that you don't do any estimation of values outside of that range. That should just be 0 instead of a percent there. I don't know why the percent's in there, but you want to make sure that you don't make any statements about weights of wolves with tail lengths less than 10 inches or more than 28 inches. Okay, that's very dangerous to do, and we want to avoid making those statements. We just want to use information or make statements about what we have information about. Now, interpreting the slope will always interpret. Okay, this just says, okay, the number that is multiplied by the predictor variable, in this case tail length, is positive 2.5. So what this means is every time we increase tail length by 1 unit, in this case that means 1 inch, then the weight of a wolf is going to what? You're going to add 2.5 to it. So you're going to increase the weight of a wolf by about 2.5 pounds on average. So for each additional inch in tail length, a wolf is going to be about 2.5 pounds heavier on average. And again, we know it increases because it's positive. A couple of notes on interpretations. Okay, in general, never interpret values outside of the range you use to build the model. So the first thing you should always do is go back and make a note of where your x value was the smallest and where it was the largest. Okay, many examples lead to models where it's really not appropriate to interpret the y-intercept because x equals 0 is not in the data. We'll always interpret the slope parameter though. Okay, that slope estimate we're going to always interpret. Sometimes due to the units of measurement for the predictor, the x variable, I might use something other than just let x get bigger by 1 unit. In this case, an additional 1 inch in the length of a tail, okay, isn't that, large or small of a change. So in that case, increase by 1 inch made sense. But if you're talking about the weight of a vehicle and gas mileage, for example. I don't want to increase the weight of a vehicle by 1 pound because that's probably whether you carry a bottle of water with you or not. That's very insignificant. What I might do is increase it by 140 pounds or something. And that would be like the weight of having an additional person in your vehicle. Uh, if you're talking about something which changes very slightly, right? So, perhaps if you're looking at value of jewelry, okay, for example, diamond rings. Well, as much as the women might like to increase the size of the diamond by a whole carat at a time. Um, a lot of people can't afford that great of an increase. So you may increase by an eighth or a tenth or a quarter of a carat at a time. So, an increase of a quarter carat in the size of the diamond ends up increasing the price by a certain amount of money. So in that case, a 1 unit increase might cover like most of the rings that are on the market. So as a result, you may increase by something a lot smaller. So it just depends on the scale as far as how you interpret the slope. But in general, increasing by 1 unit is the way we think about it from an algebraic perspective in many cases. And as long as a 1 unit increase is fine, if you increase by something other than 1 unit, you just multiply the slope by that. So if I increase by 5 inches in tail length, I would take 5 times the 2.5 and say the weight increases by about 12.5 pounds every time you add 5 more inches to the length of the tail of the wolf. So hopefully that gives you an idea on how to apply interpretations.